Welcome. We're going to look at the motion of a particle from the lens of rate of change. So let's look at this function that models the displacement in meters of an object moving on a straight vertical line, and it's given by s of t equals t cubed minus 6t squared plus 18. So the first thing we want to do is find and interpret the velocity of the particle at t equals 2. So we know that velocity is in essence the limit as t approaches 0, the change in position over the change in time, which tells us that velocity is simply the derivative of position. So in this case, our velocity would be equal to the derivative of, with respect to time, of t cubed minus the derivative of, with respect to time, of 6t squared minus, or plus the derivative with respect to time of 18, using the sum rule. Applying the various rules there, we find that our derivative is 3t squared minus 6 times 2t, so 6 times 2t is 12t, and the derivative of 18 is 0, so I'm not going to write anything for the plus 0. So there is our velocity function, and then we were asked to find the velocity at t equals 2. So velocity at time 2 is going to be equal to 3 times 2 squared minus 12 times 2. Now let's go back up and look at this definition here for velocity. Now change in position, we know that our displacement is measured in meters, so delta S has units of meters, and delta T has units of time. And initially we're not told what the units of time are. Let's go ahead and impose that right now and say at 2 seconds. Okay, so when we come down here and we're looking at our velocity, we end up with 3 times 2 squared is 12, and 12 minus 24 is negative 12. And now we need units attached to this, and this would be meters per second because of this original ratio in the definition of velocity. So now let's go ahead and interpret that. So what this velocity is telling us is that at t equals 2 seconds, so at a specific point in time, the particle is moving in the negative direction. We know it's moving in the negative direction because of the negative sign. And in the presence of a vertical line, the negative direction is downwards. And it's moving at a rate, and that rate is 12 meters per second. So our interpretation is at t equals 2 seconds, the particle is moving downward at a rate of 12 meters per second. Now let's take a look at when is the velocity of the particle equal to 100 meters per second, and when is the particle at rest. So we already found that the velocity of our particle is the derivative of displacement, or ds, dt. And that was equal to 3t squared minus 12t. So to find out when the velocity is equal to 100 meters per second, so part 1 here, we need to, in essence, solve the equation v of t is equal to 100. So that means 3t squared minus 12t is equal to 100. So we're going to be cautious. We're not going to first factor 3t squared minus 12t, which would be 3t times t minus 4 equals 100. We are not going to do that because there are actually an infinite number of solutions to that equation. There are an infinite number of ways that we can multiply two factors, 3t and t minus 4. There's an infinite number of ways we could multiply those two numbers and end up with 100. The only number who has a unique property in that we can clearly define what the two factors are is if we're looking at a right-hand side of 0. So recall from algebra that a times b equals 0 if and only if either a or b equals 0. There's no other way to multiply two factors and get 0. One or the other has to be true. We cannot say the same thing about the number 100. So we need to set this equation equal to 0. And we'll do that by subtracting 100 from both sides of the equation. So 3t squared minus 12t minus 100 equals 0. And then we can think about factoring and so forth, but there are no common factors among the coefficients. And so probably the most reliable strategy would be to use the quadratic formula. So we'll go ahead and do that. So t will equal plus or minus, getting ahead of myself, the opposite of b, so the opposite of negative 12, plus or minus the square root of b squared, so negative 12 squared, minus 4 times a, which is 3, and b, which is negative 100. That whole expression all over 2 times a, which is 2 times 3. So that means t is equal to, this now becomes a positive 12, plus or minus the square root of negative 12 squared is 144, plus we've got a minus and then the negative 100, so that becomes a plus. And then we've got 4 times 3, which is 12, times 100, so that's 1200, all over 6. Continuing, we have t equals 12 plus or minus the square root of, let's see, 1200 plus 144 is 1344, all over 6. This leads us to separating our numerator. We can rewrite this as 12 over 6 plus or minus the square root of 1344 over 6. Now we're going to take advantage of the fact that 1344 can be factored as 64 times 21. And so we're going to get t equals 12 over 6 is 2, plus or minus The square root of 64 is 8, so we'll bring that out of the square root. And that leaves 21 under the radical, so 8 times the square root of 21 over 6. We can simplify the 8 and the 6, so we get 2 plus or minus, dividing both by 2, we get 4/3 times the square root of 21. Now at this point we need to think about what these solutions represent. So we have basically 2 times. One is 2 minus 4/3 times the square root of 21. And we have t equals 2 plus 4/3 times the square root of 21. Well, let's think about the size of these numbers. The square root of 21, that's bigger than the square root of 16. And the square root of 16 is 4. So if I think about this, 2 minus 16/3, let's just assume instead of 21 we had 16, but 21's bigger. 2 minus 16/3 is bigger than 2. And then instead of having using a 16 under our radical, if we truly had 21, we're even subtracting a bigger number. So what happens is this number is negative. And so we're going to disregard it because it's not going to help us think about the motion of this particle as it moves through space. So we're left with our solution being t equals 2 plus 4/3 times the square root of 21. And that means t is approximately equal to 8.11. And I lost my units there, so let's go back and put them in. The units of time we imposed were seconds. So t is approximately 8.11 seconds. Now the second part of question B is, when is the particle at rest? Now if a particle is at rest, so at rest means the particle is not moving. And if the particle is not moving, what can we say about its velocity? Well, if it's not moving, then we would anticipate that its velocity is equal to 0. In other words, it is moving at a rate of 0 meters per second. And so what we want to do is solve the equation velocity equals 0. So to do that, we take 3t squared minus 12t and set that equal to 0. We can factor that. A common factor in both terms is 3t. And when we factor that, that leaves us with a t minus 4 as our second factor. That equals 0. The solutions to that equation occur because either 3t equals 0 or t minus 4 equals 0. So t either equals 0 or t equals 4. So when is the particle at rest? The particle is at rest at t equals 0 seconds or at t equals 4 seconds. I hope this is helpful.